Cool beans. Okay, so my plans for today really briefly are, I want to go over the logistic classifier. I know we've gotten a couple questions about it, and I feel like it's a really, really cool concept. And just because we're starting to move on to, I know next week we're going to be covering like neural nets, and so we're getting into some really cool sort of classification techniques, but I just kind of want to cover this because I feel like there's a lot of basic good stuff there. And then after we do that, I really also want to kind of take a step back because I feel like we sort of brushed over a lot of kind of core concepts of around like gradient descent and learning models and loss models. And I kind of want to just really kind of get under the hood of these things today. And hopefully by the end of class, you'll have a really, really intuitive sense on precisely kind of the mechanics of how a machine learning model learns, how it converges upon a solution, like how all the different pieces that we've been talking about and throwing around in class, like all of that happens. So that's generally my plan for today. Hopefully we're not going to do that. And of course, then we're going to do the meme contest right at the end. So that's my plan. Before we dive in, any just kind of logistics questions, course, homework, projects, things like that. Oh, by the way, we will be releasing homework 1 grades today, I think. I don't think we had some late submissions, so they had to go back and grade those, but then like everything I think has been taken care of. So those will be going out. So yeah, any questions? All right. Ladies and gentlemen, start your engines. What happens if you submit it late? The meme? Oh, that's a good question. Well, sadly, I'm going to have to cut you off. Oh, the homework. Oh, which homework? Homework 1 or homework 2? Homework 1. Okay. So that's a question specifically for the professor. The TAs can't really adjudicate late submissions, for better or worse. So I think you've emailed. I think there's been an email about that. But yeah, whatever the professor says about that is kind of how we're going to handle that. I don't know if that answers it, but that's kind of where we're going with that. Any other questions? Okay. All right, let's do this. Let's dive in. So logistical classifiers. So at this point, sort of in the lecture, we had sort of migrated away from linear regressions and we had gotten into classifications. And I think at this point, you probably have a pretty intuitive sense on the distinctions between a regression problem where you're trying to predict a continuous value along a spectrum versus a classification where you're choosing one or more discrete values, right? So and sort of, I think you can kind of intuit the differences in approaches and the strengths and advantages of different things. But I think it's worth kind of taking a step back and talking about, why we take these different approaches to classification exercises specifically. So why is it, why can't we just use linear regression as a classifier? And by the way, people do try to use linear regression as a classifier. You can try to use it as a classification model. It's not particularly effective for reasons we're going to get into shortly, but it is something that happens. And I think it's kind of worth just, again, even though at this point you probably have a certain intuition about this, let's still just kind of dive in and hopefully sort of nail that out. So, again, what if so here's an example here. We're looking at tumor size, right? The relative size of a tumor, and then we want to determine malignancy of that tumor. So they're looking at cancers. Is the tumor malignant? Yes or no. It's a binary classification model. And as we can see, the data has these kind of nice discrete classification segments. So if we took a linear regression approach to this, we would obviously fit a hyperplane to this. Again, in a 2-dimensional model, a hyperplane just happens to be a line. And that would sort of try to kind of minimize the different distance between these points. Now, the question becomes what comes next and how do we interpret sort of the resulting model? Because the problem is this line doesn't say anything. The most it says is about sort of relative proximities and goodness of fit. It doesn't say anything about the associated underlying probabilities of where these points fall. And as a result, we don't really have a meaningful threshold for where to kind of assign our classification, right? If this is 0, this is 1, somewhere in this area, we kind of have to take an arbitrary value and we say anything valued above this is going to be a 1, anything valued below this is going to be a 0. But again, because we're not looking at this probabilistically, we don't necessarily have a meaningful way of sort of establishing where that is. And you may say, oh, well, why don't we just look at this proximity-wise? Why don't we say, okay, whatever it happens to be closer to? But if you recall, that's sort of the approach we take with KNN models. And for that, we're using the underlying data. We're not using the model. Because remember, when you're using a linear regression for a prediction exercise, you're using this line. You're using the resulting line to make a prediction. So at that point, you've abstracted away the underlying training data, and you just have that line. So again, you kind of come back to that function, like what's a meaningful point along here to make that distinction. The other thing that's notable is that taking a linear regression approach, these models can be heavily influenced by outliers. And so this is an example of this. We had this nice little model here, and it kind of seems like you can do a nice little break here. Then we get this outlier here, and suddenly the slope of our line changes dramatically, and suddenly our malignancy line also kind of changes pretty dramatically in terms of what would be classified where on this. So clearly, for any number of reasons, trying to use linear regression as a classifier is clearly not a great approach. And so for a number of reasons, we want to try and change that. So we do that by sort of transforming our linear regression into a logistic regression. And there's kind of a couple of discrete sort of concepts that we're doing here. So let's talk about what's happening, what this transformation is, and what the resulting thing is telling us. So the first thing we're going to note is that we're going to squeeze our regressionary model into this logistical function. It's also known as a sigmoid function that kind of compresses outputs into sort of a 0 and a 1 output. And this is sort of a high level of the model. We're going to get into what exactly that is. Now, it's kind of worth knowing just as a background that I think is kind of interesting that the sigmoid function was developed originally by epidemiologists and statisticians who were trying to kind of look at population growth. And so the idea was it wanted to look at sort of perturbing sort of local circumstances that would lead to exponential population growth within a domain that would then kind of level off as resources and utilization was sort of maxed out. So that was kind of the trend pattern that this model was originally designed to capture with these things. And we've kind of then stolen it and used it here to try and do binary classification, but it wasn't ever initially meant to do that. And I think that's kind of just a cool way of how you can kind of like cross-disciplinary steal different approaches and ideas and conceptual models to build your own thing. So again, it's designed to sort of map an output. So you can sort of take any sort of distribution, you can map it along this X-shaped curve that pushes values in the extremes to 0 and 1 with a sort of a very steep sloped transition curve, and then models whatever the transformation term as an exponential thing, transformation of, help me guys here, is this Euler or Euler? I actually never knew how to pronounce this number, but whatever Euler's number, anybody?
Euler.
Euler?
Yeah, it's Euler.
Euler, okay. All right, yeah, Mani's saying it's Euler too. Anybody not think it's Euler? Anyone want to fight me on that? Okay, Euler's number then. So how do we kind of take our nice little learned linear regression model and kind of apply it to that? So the first thing, so we have here our nice little linear regression model. We have our output classifier label, we have the coefficients and sort of our learned model. The first thing we do is we want to model classification probabilities rather than actual sort of discrete proximity terms. Because remember, one of the things we told here is that like the relative proximity isn't a useful thing. Saying that this is valued at 0.5, 0.7, 0.3, that's not meaningful from a classification thing because that's not actually telling us anything. What we really want to be mapping with that is the probabilities associated with it. So if you have a probability of 0.5, that's a meaningful distinction, right? That's something we can build a decision function around ultimately. So the first thing we're going to do is we're going to render this in terms of probabilities, and then we're going to cast that in terms of this logistic regression. So we're doing these two kind of things concurrently. Is we're rewriting this in terms of probabilities. In this case, it's the probability of a positive label, and then we're casting that in terms of this logistic function. So we're forcing those probabilities within this distribution. So those are the two things that we're doing. Now, how do we then kind of interpret that? So then again, the output of this model is the probability of the label. And then immediately that's a much more useful thing for the purposes of classification. You can either use those probabilities directly, or you can define a certain threshold value. And you can then decide, and that can be your sort of your linear decision boundary. And I'm going to come back to that in a little bit. But it's the idea that you can, once you have those probabilities, you can set a discrete point. You can say, okay, probabilities above this rate, we're going to classify as 1. Probability below that, we're going to classify as 0. Then, and remember, this is also kind of something that we've been playing around with, particularly when we're looking at like the area under the curve and looking at like our ROC curves and those metrics. This is really where questions about like sensitivity, recall, error sensitivity, things like that come into play. Because once you've modeled out your relative probabilities, you then, as the master modeler, get to decide how strict you want to be in terms of your permissions, in terms of what kind of predictions you allow in, and in terms of what sort of errors you allow in. And remember, this is where we talk, so if you recall, sensitivity is your type 1 error. It's your false positives. It's how many times do you predict a label and that label turns out not to be true. Recall is your false negatives. It's how many things out there should you have predicted as positive, but you just failed to do so. And ultimately, the sensitivity that you have to sensitivity recall sort of comes into, oh no, I'm sorry, that's precision. Okay, that should be precision. The sensitivity, precision is your type 1 error, recall is your type 2 error. Okay, just doing spell check on the fly here. But yeah, depending on how sensitive you are to those things will depend on where you define that decision boundary. How many kind of certain errors are you going to allow in? It's also worth noting that in terms of the results that are sort of reported out, logistic regression specifically uses the results is also known as sort of an odds ratio, where you're sort of casting the probability of spam divided, not spam, this is an example, the probability of a label divided by the probability of not that label. Okay, and then like we've said, we've already discussed that because it's that probability ratio is then rendered on that sigmoid function, it kind of forces it into that binary classification. One final thing that I think is kind of a nice thing to note specific about logistic classifiers is that they are they're better able to sort of capture outliers without skewing the model. And you can kind of get an intuition of this because of how, because the sigmoid function, right, has it's, oh, bollocks. What's it called, guys? I'm sorry. What's it called when you have a line that sort of approaches a space, but it doesn't actually hit it?
Asymptote?
It's asymptote. Thank you. Yes. So because the sigmoid function renders things asymptotically, so you'll approach the 0 and you'll approach the 1, but you never actually fully hit them. It kind of captures outliers really, really well, and it kind of builds them into your model without skewing the overall distributions. So that's kind of another nice feature about it. So again, so there's a question in the chat about sort of how does it calculate the likelihood. So remember, here's I think the two kind of things to note with it. It's really doing two things concurrently. The first thing to note is it's taking the probability of it, and then it's casting that probability within the sigmoid function. So the sigmoid function itself isn't doing the probability, but what you're doing is you're taking your logistical, you're taking your linear regression, you're using it to assume probabilities, in this case, the probability of y equaling 1, and then you're rendering that in terms of a logistic function. And so I think that's the distinction of what it's returning here.
So we're assuming then that the probability can be modeled by a logistic function, right?
Yes, and exactly, and we do that specifically to achieve this kind of this binary classification result. So we're really doing two discrete steps, right? We're starting out by saying here that just rendering sort of line on curves is not meaningful. We need the associated probabilities associated with sort of relative classification. And then once we have those, we're then rendering them on a sigmoid function that then kind of allows us to collapse what would be sort of discrete probabilities into sort of binary classification. So we're really doing it's kind of two steps. So okay. So then once you've kind of rendered that, once you've done that, then as I mentioned before, you have your linear decision boundary. And that's sort of something where you can sort of along that function here, you can sort of set what probability you're going to allow to classify either way. And again, a simple example, you can do a 0.5 as your divider. Anything greater than 50%, you'll do is you'll assign the label, otherwise you won't. And it's kind of worth noting because we talk about linear classifier models, and logistical regression is one of them, SVMs are another. But if you think about how they actually work, neither of those are generally speaking linear the way we would think about a linear model. They're linear only to the extent that they learn a model of your data and then apply a linear decision boundary to it. And I think that's kind of an important distinction to make. But we don't actually, the model itself isn't linear. And I just kind of want to make that clear because I think it can be confusing to talk about linear, linear classifications and whatnot, because these are linear, but they're linear because they have linear components. Unlike, say, Bayesian models, which there's nothing intrinsically linear about that. Unlike, say, a KNN, which again, nothing intrinsically linear about the resulting decision boundaries. So that is logistical classifiers in a nutshell. You have at this point sort of done them to death multiple times in the code. Hopefully you're sort of feeling a little bit better about it. I don't think from a conceptual standpoint you're going to need to know anything more than that. In fact, this is probably more than you'll need to know for any kind of exams or even projects. But I did just kind of want to mention it because I think it's kind of a cool way of, again, transitioning from thinking about regression to classification and thinking about how things like probabilistic models become so critical for classification and how we kind of make those transitions. So let me pause there. I don't have in fact anything more to say about that, but I did just want to kind of throw that out there. I don't think you're going to touch on that. The halfway point of okay, so there's a question about the decision boundary for logistic regression would be a halfway point of a linear regression. So yes and no. So there's two things to unpack with that. So the first thing is that the decision boundary is, you could think of it as being similar to the halfway point, but the first thing being that you can define arbitrarily where that decision boundary is going to be, again, based on your recall versus precision, right? If you want to make sure you're getting all of your true positives, you can set your decision boundary super low. And it doesn't necessarily have to be the halfway point. And then the other thing to know is, again, that unlike the linear regression where it's just sort of relative positioning on your regression line, here, what you're essentially plotting is your probability. So I think those are the kind of the two distinctions I would draw. But other than that, conceptually, yes. Good question.
Wait, so to clarify, and like the quote unquote halfway point
Yeah.
of the logistic regression is the same as the halfway point of the linear regression.
Yes, again, with the caveats that, with the caveats that, again, here you're looking at just relative position on the line, which is the predicted actual value, versus a probabilistic value, which is what logistic regression is looking at. But yes, ultimately, it would be functionally the same. And oh, by the way, I am taking a peek and we have our first meme submission in the inbox. Okay, so yeah, so for those of you who are working vigorously on that in the background, just know the competition is heating up. Yeah, email the memes to me, and let me just go back here really quickly. Just shoot me the email. And then, like I said, once we get through the material, I will collect all the memes. I'm going to put them right on the end of this deck, and then we will vote. Okay. So deep breaths. We're going to pivot a little bit. Now's the time to kind of take a big sort of conceptual step back, because all this time, so you'd be running your right. You'll call up, let's say, like a logistical classifier. You'll set your logistical classifier model. You'll say it's a logistical thing. Then you're going to call your fit function to train your model on your training data and your training labels, right? There's that fit function. Then once you have it trained, you then call it on your test data to get your predicted labels, right? There's that step. So what I really want to talk about today is that fit function, what the heck that is doing and how that's doing it. Because again, I think that underlies so much of what we're talking about here, and having a sort of a conceptual understanding of it hopefully will sort of just make everything a bit more intuitive going forward in the class, particularly as we get into sort of more abstract learning methods. So this was something we sort of talked about last week. We already kind of talked about it today a bit, but again, there's kind of this two sort of steps to your, for most learning models. We say that, your model is going to learn something about the training data in order to better enable it to classify. And then it applies sort of separately, it applies that decision function to actually classify. And so, like with the logistic regression, it learns the associated probabilities and then it casts them onto that sigmoid, that sigmoid function, that distribution. An SVM model learns the hyperplane that will sort of carve your data into two, right? So it's learning sort of an abstracted pattern, an abstracted model of your data. And then with that model in tow, it then sort of makes a decision in terms of how to apply classification. And then, okay, we don't really need to talk about that bullet point because we've already talked about it today. But again, we can our decision function, we can manipulate very easily, just depending on the types of errors we want, the types of things we're willing to sort of allow in our model. But again, today we want to focus on that first thing, the learning side of things. And to do so, we need to talk about two things. We need to talk about your loss functions, which we've already sort of talked about in lecture, but I kind of just want to formalize that. And then we want to talk about your optimization functions, like gradient descent functions. So, okay, loss functions. Again, at this point, you guys should have a general understanding about sort of a loss function. We spent a lot of time talking about it with regards to regression, but a loss function is basically just how you keep score of how your model is doing. It literally is your scoreboard. And for a loss function, generally speaking, we want it to be lower, right? If you're modeling the amount of error that your model is generating, you want to try to minimize your loss function. And so part of like the whole process of learning is minimizing the loss function. That's really sort of the ultimate goal of this. Now, regression and classification will use different loss functions. Sometimes they'll overlap, but oftentimes they won't. We've conceptually sort of dealt with a number of regressionary things, MSE, MAE, right? Sort of looking at, if we're looking at a regressionary model, just looking at error. We've talked about how we can sort of penalize different types of errors. Whether or not we sort of treat errors uniformly the same, whether or not we disproportionately penalize errors that are sort of that are widely divergent from our predictive values. So we talk about that. Classification, we can use things like MSE for classification as well, because you can just kind of at a very simple level look at it like a 0-1, and if you predict wrong, right, that there is a physical error, a physical offset, so you can look at those too. But we also like to look at these in terms of probabilities. And so a lot of the ones that we look at specifically for classification leverage that. So just a few I want to call your attention to are likelihood loss. It just kind of takes the predicted probability example, multiplies them versus, and it sort of pairs it against the actual result. Log loss, I'll shoot the next slide. We'll kind of dive into a little bit more, but I'll just throw out there that this is probably the most popular loss function for classification exercise. It's typical, like if you go on like a Kaggle competition, log loss will typically be the loss function they're going to use to judge how well your model performs. And just simply, we take the likelihood loss thing and we apply a logarithmic transformation to it. And let's talk a little bit sort of conceptually about what a log loss does and how it works. So again, we're looking at we're penalizing the degree to which your model predicts a label compared to what the label actually is. So if you want to look just conceptually at how sort of a resulted log loss thing is. So this is we're looking at the associated penalty when the actual label is 1. So as you can imagine, if the predicted probability is 1, i.e. you have predicted with strong confidence that it's going to be a 1 and it actually is a 1, it's converged on 0. As your sort of associated probability goes down, the error sort of starts to kind of creep up. Your loss function starts to creep up, right? By the time you're getting to only a 40% associated probability of that labeling, you're getting some kind of error there. But here's kind of the cool thing about log loss, and here's sort of why it's sort of a neat approach to this. You notice that it doesn't treat sort of probabilities uniformly. In fact, it treats sort of an incorrect probability exponentially. And so the idea here, much like, if we take a mean square error, how we're disproportionately penalizing sort of big errors, a log loss disproportionately penalizes incorrect probabilities. So it's not just about you incorrectly labeling it, it's the degree of confidence to which you have incorrectly labeled it that matters. So in this case, as your confidence in the incorrect label increases, your associated penalty increases significantly. So again, so like a log loss will say it's okay to get it a little bit wrong. It's okay to be a little bit uncertain, but just don't be really certain about the wrong thing. And so that's kind of a cool thing about how a log loss function will sort of render and evaluate how your model performs. It's not just about did you get it right, did you get it wrong, right? It's not just a simple kind of is the label right, is it wrong? It's looking at the underlying probabilities and it's saying, okay, to what degree when you made this probabilistic decision, how confident were you in that decision? So again, I think that's like just a really cool conceptual way about thinking about error terms in your associated model. Let's see. So, and again, this is something we spent a lot of time talking about last week. So if your goal, when you are training, your goal is to minimize your total loss function, your aggregate loss function. We talked about, like, is it always the best idea to uniformly minimize the loss function? No, as you are probably bored to tears about. Overfitting is a problem, and we are generally not fond of overfitting. How can we resolve this? We spent a ton of time last week sort of talking about that. Changing our loss function to penalize overfitting by regularizing it. It's not even a word. So by adding L1 errors, L2 errors, ridge, lasso, everything that you're kind of going to have fun with on homework 2. So you're going to be dealing with that to try and kind of make sure that, yes, even as you're converging on a minimum loss function, you're not doing it by overfitting. You're doing it in a way that'll generalize to the universe of data. So I think sort of conceptually, you guys are with me on loss functions. Again, it's just how we keep score. We're trying to get the minimum score. When we minimize, it is good. The problem, and this is kind of leading into our second thing, is so I plug in some values, right? I plug in some coefficient values to my things. I get a loss function score. What now? How do I, in the universe of potential permutations to my model and the various ways in which I can adjust my weights and everything, how do I kind of do this in a way that kind of arrives at a minimum thing? Do I just plug in values at random and see, do I just randomly sample 1,000 to 1,000,000 possible permutations and just choose whatever the minimum result happens to be? Do I do an exhaustive search? Do I literally map out my entire universe of multifactorial permutations and just systematically search through them? Or is there kind of another way of me navigating my loss functions in a way that I can kind of, again, arrive at my minimum possible value? And spoiler alert, there is. But let me just kind of pause there. And before I stop talking about loss functions, see if you guys are feeling good about that concept. Is there any questions specific about loss functions? Is log loss same as log likelihood? I think so. There's a question in the chat about log loss being the same as log likelihood. I believe it is, but I have to Google that to make sure. Because again, log loss is you're looking at probabilistic approaches with it. So I believe it is the same, but until I would have to Google that to make sure. But yes, I do believe it's the same. And if somebody wants to Google in the background and let me know, please do. So yeah, so I don't go into too much detail about this, and I'll be honest with you, I don't. I only know it at a high level, so I don't want to tell you that like and I don't think for this course you would need to know anything more than this at kind of a high level conceptually. But from what I understand, you're just simply taking the predicted probability for each potential input. You're multiplying it, and then I think you're sort of comparing it against the actual input. And so then all you're doing with a log loss or a log likelihood is just kind of rendering that logarithmically. So again, so the way it's sort of looking at this graphically, and I'm sorry that I don't have sort of more details on this. I'll be honest with you, I sort of only did this at a very high level, and so you're probing to a point where I don't know that I can answer authoritatively on it. But again, what I can say is that it does look at the I think because okay, so he's throwing up against the probability of. Sorry, let me just read what you're throwing in the chat. I think you get it because for the data point X with true category Y1, you multiply. Yeah, so I think that's correct. Yes. So because you're looking at like the actual label being 1, and then you're getting the associated predicted probability of it. And so wherever the associated probability is less than 1, you can kind of think about that that distance as being sort of a loss. So it's not, in this case, we're not looking, because it's not just a binary 0 or 1. What we're looking at here is how close is my probability to the actual label. And that distance is sort of the error term in there. Ideally, if your model was absolutely perfect and did everything right, not only would it be classifying everything correctly, but it would be correctly predicting everything with 100% probabilistic success. And obviously that never actually happens. But it's the idea that there your loss isn't just 0 to 1, but it's, oh, my thing predicted, let's say, a 75% chance that this is a 1 versus 100%. So that's a little bit of a loss there. And that's simply doing it. And then a log loss is, again, just simply transforming that approach logarithmically such that it disproportionately, right? The further away you get from your predicted probability from your actual label, the way it sort of disproportionately penalizes it. So again, a log loss or a log likelihood thing, it says it's okay to be slightly unconfident about your things. It's okay to have an 80% probability of a label, if that's correct, but just don't get it really wrong. So hopefully that kind of gets at it. And Mani, thank you for probing me on that. Okay, so then Kadar has a question. Basically, we want to always minimize our loss function. Yeah. So again, we want to, and this is kind of, we go at this at, I'm not even going to touch that one on the chat, dude. But yeah, so Kadar, to your question, we talk about this a lot. Like we want to, right? We do want our model to sort of, we want to minimize the loss, but we want to do it in a way that like creates a model that, again, will generalize, that won't sort of learn the specific nuances of our particular data set to the point where it has overfit to that data and then just simply is not actually generating a model that will be universally applicable, but is just picking up whatever weird tweaks and outliers in our own data. And so the regularization is, it's kind of, again, it's like putting the brakes on it. You're saying, okay, we do want you to try to converge. We want you to try and do well on this, but, let's do it in a way that makes sure that this model will be generally consistent. So, all right, so then kind of getting back to this idea. So now we know how to keep score, right? So we know if we're doing well, we know if we're not doing well. But the next step of this is saying, like, how do we actually navigate this approach? If we're trying to kind of get our model to sort of converge on this thing appropriately, how do we do this in a relatively efficient manner? And so now it's time to kind of think about this in terms of your calculus. And, oh, why is this not? This is supposed to be like a nice GIF file. Okay, well, I'm going to exit so you can kind of even see this. But intuitively, we can think of slopes, right? We can think about derivatives. And that's kind of what we're doing, right? So you had to actually do this already. You had to sort of render it in terms of the partial derivative of these things. But let's say, so we have our model and we have our loss function. And remember, our loss function is rendered in terms of our model. So all we have to kind of look at is, if we look at the slope of something, we not only have the actual value, but we have the relative position of sort of how it is changing, right? That literally is what the derivative of something is looking at, the change of your overall loss with regards to the change of the particular weights. So when you solve for those partial derivatives, that's particularly what you're looking for. And that gives us, again, that kind of basis to think. And so it says, like, you can not only know the directionality in which it's changing, but you can also know the relative magnitude, the steepness of the associated slope. So generally speaking, like the steeper your slope is, the faster your model can learn. But as the slope approaches 0, your model is going to stop learning. Right? Sort of conceptually, once we have reached 0, we've effectively flattened out. It's a point at which we can say, hey, okay, this is the best we can do. And generally, that's kind of exactly how this gradient works. We're going to initiate at some value. Typically, it's sort of a random initiating. And we start at that point. Then, looking at the partial derivatives, we adjust the parameters in the steepest downside direction. And we keep traversing it, keep traversing it until it reaches a point where we've effectively minimized it. Once it flatlines like that, that's what we know of as converging. And let me get this off things. You can see. Isn't that supposed to be? Is it this one? Oh, it's this one that does it. Okay, never mind. Cool. Okay, so okay, yeah. So again, like let's say we have initialized here. So your gradient descent function will look at this and say, okay, well, I want to again ride that gradient. Literally, think about this like skiing a slope. You just want to ski downhill in the fastest possible direction. I'm going to go there, there until I converge down there at the point at which my loss function is overall minimized. Now, as you will notice, certain discrete steps are taken. This isn't a continuous process. We're taking certain hops. We're hopping. And that hop is important because the size of that's what we call a learning rate. And there's an optimization step there as well. So like everything else in data science, there's this Goldilocks thing, too large, too little. If it is too large, you get into the scenario in which you can overshoot your minimum. So this is kind of an example here. On the rather than like hitting our target thing, we kind of get to this point and then we start just bouncing around it. And we never actually kind of hit that real convergence because we have just had, because we're taking too large jumps. Too small, if we're taking, if we're sort of jumping this too small thing, then computationally, this becomes this can become a very difficult problem. And hopefully you will intuit exactly right. Like right now, we're looking at these nice, beautiful, kind of really easy gradient descent functions. So right now you're like, it doesn't seem so bad. In a moment, we're going to start looking at some models where you're like, oh, actually that could be a problem. So if this is too small, if each training step becomes too small, again, it can just become overly intractable and your model can get stuck on suboptimal outcomes. So generally, and this is kind of something I want to mention here, typically we never may actually reach the exact minimum value, but typically we'll kind of hit a valley where precisely like this, we'll kind of be oscillating around in the proximity of it. And at that point, we're going to stop our iterations when, one of two things happen. Either our loss values haven't improved, or we sort of, so either like our function just over a series of things, we don't get any more improvement, or we've sort of flattened out in terms of or we sort of arbitrarily stop our model. We say, okay, you have a certain number of iterations to do this, a certain number of modifications to make. At that point, if you haven't converged, you just return your ultimate thing. And that's exactly what we had you do for project 2. That max iteration was precisely saying, let's have you run for a little bit. And then at that point, if you converge, great. If not, no. So, okay, so let me pause there and just kind of throw that up there and ask, like, okay, in terms of like how a gradient descent, and by the way, we're going to spend more time talking specifically about like that learning rate and everything like that. But just at a high level, are you guys feeling like how a gradient descent works, like how it's leveraging those partial derivatives and sort of migrating, and the importance of like the learning rate in terms of like hopping and approaching that? Okay. All right. So you guys are feeling that? Cool. So then let's throw a complication. Let's throw a little bit of a wrinkle into it. Because again, we had our nice little, this is beautiful. We have this one nice little minimum here. We can just nicely smooth down. All of it looks good. Do multiple descents from various. Okay. Okay, good. Okay, great. All right. So yes. So there you go. So we have this concept called local versus global minimums, multiple minimums. So the problem is, and up until this point, we've sort of only dipped our toe into the relatively shallow end of these things. But when you start talking about really, really complex models, when we start getting into things like convolutional neural nets and things like that, your loss function starts to look very funky. So, and you can kind of see this here. You may have an issue that we call local minimum, where indeed you will find, like here's an example here. If you ride your little gradient descent function down here, you will arrive at a seeming convergence. Your point will, you will converge, you won't be able to improve, everything looks good. But the problem is, overall, your performance is really not that great. And in fact, again, here is this notion of like a global minimum, that there's elsewhere in your model, you will have the actual real minimum value. But the problem is, because you've just you happen to initialize here at A, you just happen to run there. Whereas if you had initialized here, you would have gone down here. And as you can see, these models can become incredibly, incredibly complex. So this is, again, I found this visual representation so that they kind of rendered a 56 layer, the loss function for a 56 layer convolutional neural net. And as you can see, like this is just an incredibly complex loss function. So how do we deal with this issue? Because this is obviously a non-trivial problem. And again, particularly as you get to more and more complex learning models, your loss functions are going to begin to resemble this and not this beautiful, simple model. So in order to deal with that, we need to introduce a little anarchy. We need to be, right, if before we had a nice little, if we had a nice little clean progression to our minimum, we kind of have to shake things up a little bit. And so how do we do that? We can do it one of two ways. We can change the way in which we sort of calculate our gradient descent. And the other thing that we can do is we can alternate our learning rates. And let's kind of go through how each of those strategies can kind of get at throwing in a little chaos of things. The first thing is sort of how we sort of adjust our thing. Because remember, our whole model with this is we take this point, we sample what our error is, we sample that relative term, and then we adjust. Then we sample again and we adjust. So there's an interesting question there about what exactly we are sampling. And we can do sort of one of two approach. The first thing is we can do a batched approach, which says, let's take, remember, we have all of our training sets. Let's say we have 500 training examples. We can run our entire model using we can plug in our entire training set using our current model. We can sum the loss over all possible examples, and then we can make an adjustment. The opposite extreme of this is we can just pretty much sample things at random. We can sample individual training values. And then just based on that one particular instance, we can try to update our gradient each time. So how will that impact our things? So a batched approach will tend to get very nice, smooth convergence things because you're taking the average, because you're looking at their error terms over sort of the course of an average. We will tend to sort of get a nice smooth convergence. It'll kind of tend to have that nice, again, using this graphic here, it'll tend to just kind of float down there in a very smooth and continuous manner. Oh, yeah. What?
All the fours are different.
Oh, okay.
They're like different combination of different like jams.
Okay.
And butter.
Cool. Great.
So mix and match.
Okay, great. Okay, awesome. Sorry about that, guys. So if we take a stochastic approach, where again, we're kind of bouncing around, right? Where we're, maybe instead of like smoothly moving, we may look at one additional row and it may say, go this direction. Then we may take the very next row in our data and may say, actually, you want to bounce this direction. You want to bounce this direction, this direction. And kind of a cool result of that is rather than sort of nicely, smoothly approaching our thing, we may kind of like hop around. And that hopping, if you think about like visually, if you think about like the hopping thing, it may say you may start this way, but then you do another thing and say, oh, actually, I need to go this way. And then, oh, actually, I'm going this way, this way, this way, this way, this way, this way. Aha, and then I'll hit there. So you can kind of bounce around with us and may be able to extricate ourselves. The other thing that we can do is our learning rate. And this is the other kind of cool thing. So remember, we had talked about learning rates and we had talked about the trade-off in terms of computability, where the learning rate can kind of like bounce around here. And we said, you know, a problem here is that a higher learning rate may prevent you from sort of hitting the actual global minimum because you just keep bouncing around there. Well, another reason that a higher learning rate may actually be good is it can help you avoid sort of shallow gradients. So if you think about like a really large learning rate, I might just be able to kind of hop over this local minimum here. Like if you assume your global minimum is going to be a much deeper, steeper kind of approach, having a high learning rate, I may just jump over those things. Right? The thing, like to use a metaphor, you may think of this as a like avoiding the potholes, if you will, of your loss function. Am I doing that? So those are kind of two approaches we can do for that. So let's talk about some specific kind of formalized approaches to gradient descent. And by the way, this may be, this is a little Savannah meme I made specific for this. But so the first thing is a batched gradient descent. So this is just the pure batch thing, right? It'll run through your entire training example, what we call an epoch. And we will average the error over the entire thing, and then we will adjust our weights accordingly. And it only updates after your entire training thing has run. So let's think, you know, advantages, disadvantages to that approach. Advantages, computationally very efficient. As you can imagine, you're not doing that many updates. You're just kind of running these things. It tends to produce a very stable error gradient and a stable convergence. So we tend to sort of move very nicely. However, from a disadvantage standpoint, it doesn't always find a global minimum. Another kind of issue with it is it does require the entire training data set to be in memory and available to the algorithm. So there is a kind of a trade-off to that approach. Now, the opposite of that is the stochastic gradient descent. And that is the thing where it samples everything. And each row, it updates the parameters. And it's kind of like continuously doing that, randomly sampling it, randomly updating it. So again, trade-off there. We could actually get a faster convergence if we do a stochastic approach, just because you are constantly upgrading it. So every time you modify your parameters, it's possible that you will converge more frequently. The disadvantages are it is more computationally expensive because you are constantly updating your parameters, you're constantly running those updates. And it's also a much noisier, much more chaotic one as well. So, and then finally, just to kind of throw, and by the way, there are tons of these approaches. I'm just kind of throwing out just 3 as an example, but just to kind of give you a sense of just sort of the universe of gradient descent examples. There's this notion of like a mini batch gradient descent, which is kind of like a hybrid of them. So, you know, rather than doing like an all or none approach to batching, let's do literally a mini batch. I take small batches and then I will sort of perform the errors. I will do, and then I will sort of update based on the overall aggregate error of those mini batches. And the idea there is it's kind of a balance of the robustness of a stochastic approach and the efficiency of a batched approach. So that is, oh, and quick aside, I don't know if you guys are kind of familiar with this, but does anyone know like why, we don't really talk about hardware in this class, but why GPUs are so good for machine learning? Does anybody know that, like why we keep doing GPUs? So this is a sort of a parallel computing. Yeah, okay, perfect. Okay, so yeah, so Tien and Rob, you guys kind of nailed both of it, right? So the whole idea of a graphical processor unit is versus like a CPU is the idea that it's a much simpler circuit designed to kind of handle very basic computations. For graphics, it's obviously about like image rendering. And so, you don't need kind of the same sort of complexity in terms of handling a multitude of functions that you would have for a CPU. And again, like you said, it's all about the parallelism, right? Particularly when you're getting into like these neural nets and whatnot, you're going to be running sort of multiple things. And so all of these are very simple sort of updating calculations, but they're sort of run in parallel. And that's precisely why GPUs are kind of the preferred sort of hardware for these sort of heavy duty machine learning tasks. So yeah, cool. Okay, so then I kind of want to mention this, and I think I've actually gotten through the material relatively quickly here, which is both a good thing and a bad thing in terms of your comprehension. But we do about this last week visually. How do you overfit a model? Okay, sorry. Let me just quickly see this question. You talk. Okay, so sorry. So good question. So there's sort of a question about overfitting the model when converging too quickly. So there's kind of a few concepts here that I want to kind of untangle there. So thank you for asking about that. So there's the notion of quick convergence, convergence on a global minimum, and then overfitting. So maybe I want to kind of try to tease out all three of those ideas. So the idea of kind of quickly converging is the idea that obviously every time we sort of update our, every time we make this jump, theoretically gets us to converge faster. So it's a question of like, how often do we make those jumps? And if we're doing a batched approach, I'm going to run my entire training set. Then I'm going to update my parameters. Then I'm going to run my entire training set again. Then I'm going to update my parameters, training set again, right? If I'm doing a stochastic approach, I'm going to take a single instance of my data. Then I'm going to update, take a single instance of the data, update, single instance, update, update, update. So when we talk about converging faster, that's kind of the idea there, that we can potentially converge faster by doing it stochastically, because we're going to make that learning rate jump more frequently and more often in terms of just sort of computational steps. So that's the idea of sort of like quick convergence. The idea of sort of why sort of a quick convergence can or cannot help is sort of precisely the idea that like by jumping around very quickly, you can sort of, it's the idea of again, hopping, because rather than if you average results, you'll tend to get kind of a consistent performance across things. But obviously within each data point, your variance will naturally cause you to kind of jump different ways. And so it's the idea that you will theoretically, again, kind of using that rabbit metaphor, you're going to kind of hop around until you hit the global minimum, when it's assumed that it's sort of a big enough, deep enough pit that you'll sort of just naturally fall in there, and you won't kind of get stuck. Again, just to use the metaphor, you won't get stuck in the pothole of a local minimum, but you're kind of, once you hit there, even if you're bouncing around, theoretically your bounce won't be as sort of as, I guess, drastic or dramatic enough to take you out of that. And then the final idea about like overfitting is just the whole idea that, remember, this loss function is based entirely on your training data. And so the loss function may or may not be applicable to the broader universe of data. So while yes, we are shooting to hit that global minimum, that's only the global minimum for my training data. And that may, while this may be the particular thing that works best for my training data, my actual thing may be, let's say, this may actually be the best for the universe of data. So I know that was sort of a bunch of sort of different concepts, but hopefully they kind of work in parallel. So I hope you guys are kind of seeing how they interact together. But yeah, thank you for asking about that. Okay, any other questions specifically about that? So I did kind of want to mention this specifically because this was something that we also asked you to play around with in your learning model. I think one of the learning models for problem 2, we asked you to decide it for SAG, which, given that we're in LA, naturally you all went Screen Actors Guild as your first approach, but that is not what this is. It's the stochastic average gradient. And this is kind of like a cool idea. Like I said, there's like a lot of, if you look at like a lot of research in machine learning, one of like the key areas in which people are doing a lot of really interesting work is precisely in this area. Like, how do you sort of model your gradient descent function? Like, how do you navigate your data, particularly when you're dealing with these really, really complex loss functions? How do you kind of do this in an effective and efficient and computationally viable way so that you'll sort of hit a convergence point like in a relatively reliable manner? And SAG is kind of one of these relatively new approaches. So the whole idea is so you can kind of see here is the method works. So what it does is it first converges to a local minimum. It then caches the weights associated with this, and then associates the learning rate to a higher value. So let me kind of specify something here too. I don't think I mentioned this, but there's also the concept of a variable learning rate. So oftentimes, we've talked about the learning rate as being a constant, but a lot of gradient descent approaches will actually, intelligently optimize the relative learning rate too. So like when you have a very steep gradient, I'm going to say, you know what, I can take a huge hop because right now I know I'm nowhere near my minimum. So let me take a huge hop here. And then I'm like, oh, okay, my gradient's slowing down a bit. Let me take a smaller learning rate, a smaller one, smaller one, smaller one. And as it flattens out, my learning rate actually flattens out as well. So rather than getting in the situation which we're treating every sort of hop continuously, we can kind of intelligently say, as I am approaching my convergence point, my learning rate shrinks. So ideally, I will actually hit it and not sort of jump over it. So getting back to this, so the idea is essentially kind of you run your method stochastically, and then you converge to a minimum, and you do it again by sort of as you approach that thing, your learning rate shrinks. You then cache the weights associated with that, and then you sort of jump your learning rate dramatically. And then this higher learning rate will then sort of propel you out of whatever the minimum was to a random point on the loss surface. And then the algorithm then converges again to another minimum, and it repeats this a few times. And then all of these sort of predictions are then cached and averaged so that you can then sort of try to kind of triangulate and figure out what the actual global minimum is, which I think is just like really conceptually such a cool approach. So again, it's the idea like you start here, you kind of stochastically approach a minimum. Once you've hit that minimum, rather than just like halting, like rather than you just returning your condition, you like kick your learning rate way up, kick yourself randomly somewhere in the thing, converge again, cache that output, cache those weights, kick your learning up, wait again, run it again, cache, do it again, then so on and so forth, and then ultimately kind of return your value. So that's the SAG that you were running in project 2. That's what it is. And again, I just think it's like such a cool kind of approach to these things, because again, you want to get that convergence, but you need that randomness. You need that thing because you really don't know kind of in this treacherous valley of stuff. Why did you both? So, okay, so then there's a question about like why not doing the mini batch gradient descent. So where are we? Yeah, so this is going back here. So the simple answer for that is, and this is kind of the thing, is there's always going to be a trade-off, and depending on the model that you're working, mini batch may not be the best, right? Mini batch may also produce the problem of you kind of lose the efficiency of the batch, but maybe you don't gain enough stochasticity with the stochastic gradient. So while mini batch is like a good, solid gradient descent approach, it's not always the best. And you can see something like SAG being another really kind of cool approach for that too, that like takes the efficiency of the stochastic approach, but then by adding that kind of randomizer to it, by adding that, like by jumping your learning rate like that, allows you to kind of sample things more thoroughly. And a mini batch doesn't necessarily do that. And by the way, what we're talking about today is just kind of just a small subset of approaches to this. And again, just to emphasize, like if you're looking at where sort of like the cutting edge machine learning work is being done, a lot of it's being done precisely here on how do you sort of develop a gradient descent that will try to find the global minimum as efficiently as possible. There's a lot of really cool work that's being done here to that effect. So, and and again, like with all other things, data science, what works for one model won't necessarily work for the other. And it's useful to understand that there are these different approaches out there. And as you're training your own models, as you can see, it's useful to kind of try and do different solvers, to try and do different gradient descent approaches, because again, your model, what one gradient descent converges on, another may not. So it's kind of cool to have this as something in your toolkit to try and kind of work with. What are the weights? What are the average? And not select the weights from the lowest. Okay, so yeah, so okay, so there's a question going back to SAG. So the weights that we're doing it are your actual like coefficients associated with it. So essentially, you're kind of like you're caching your solution is what you're effectively doing by doing that. So you're saying, okay, here's one solution I found. Let me just cache the value, cache the loss function associated with that. Then let me run another one. Let me take a look at that. And then the whole idea being that the reason I'm then comparing is I'm not just doing, I think this is kind of the added key of what a SAG does above just saying, let me just sample a bunch of convergence points and let me look at it. It's the idea that by taking the average across these, I can kind of track overall if I'm making progress or not. Because again, within this, like if you're thinking about something with the complexity of this model, you may encounter a myriad of different loss functions. A myriad of different sort of local minimum in certain areas. And so by taking the average of your convergence points, you can kind of zero in on areas of likelihood global losses. So it's not just the idea of saying, oh, here's a loss, here's a loss, here's a loss, here's a convergence, here's a convergence, here's a convergence, here's a convergence. Let me see which one's best. And it's saying, hey, the average convergence points around here were much better than the average convergence points around here. Let me target this area to try and find a global one. So it's that added nuance of saying, I'm not just going to blindly just tally my convergences. I'm actually going to use them to try and pinpoint where the likely global one is. So that's the added step that a SAG does that I think is really cool. So the weights there, yeah. So the weights there are the actual like your model weights. Like for instance, so if this is like a neural net, where you have sort of for each neuron you have your activation function and the weights associated with it. So it's whatever in your model you're adjusting, and then you're going to cache those, and then you're going to store the associated converged loss value. So we haven't talked about neural nets, but if you want to think about this as like a linear regression, it's just the coefficients associated with it, with the result you're getting. Yeah, the parameters, exactly.
I'm a little confused.
Mm-hmm.
So you record the parameters basically and the loss value, and then you take the average of the parameters.
You take the average of the loss value, but you do it. So my understanding of this is you take the average of the loss, because again, you want to, when you think about this strategically, what you're trying to do with these things is you're trying to say, okay, I'm going to hit a bunch of local minimum, but I want to try and figure out roughly what area the global minimum is going to be. And so by taking the average of sort of different regions, if you will, I can kind of say, okay, am I getting closer? Am I getting further away from my global one? So, so let's say I'm hopping around here and I'm going to get, it's basically, I think you keep like a running average of it. And so if I'm like around, like, let's say the global minimum is this value right here. So if I'm taking a running average here, I might say, okay, well, this is, this is higher, but as I'm moving in this direction, my average is going lower. So something seems to suggest that I'm heading in the right direction. As I'm doing my like random hopping, I seem to be heading in a direction where I'm approaching what could be the global minimum. So that's the average that you're taking. It's your running average of converged loss values. And again, I think just kind of conceptually, the thing to recognize is just how massive this feature space is. Because you have to remember, when you're dealing with like these big data models where you're dealing with hundreds or thousands of discrete parameters, and you're getting into these kind of like neural net models where you're doing sort of hundreds of hidden layers, the sort of derivatives of the partial derivatives of for the loss function, right? Like just kind of visualizing just how complex that associated loss function is and how tweaking one parameter does it, it's just incredibly convoluted. And that's why we sort of have to expand our sort of conceptually our thinking around what a convergence looks like and how that the actual sort of topography, your gradient descent function is going to try to navigate. So really, again, what a SAG is doing is it's doing twofold. It's trying to give itself a little bit of a context for, as you're moving around your little local minimum, are you making progress towards a global one? That's kind of what the averaging function is doing. But then by sort of randomizing it, you're allowing yourself to kind of converge and then jump out and try again. Converge, jump out, try again. Converge, jump out and try again. So yeah, again, I know that that's like a lot here, but on a very, very simple level, again, all we're doing is, remember, we have our little loss function, it's our little scorecard. Our gradient descent is just sort of how we kind of navigate that loss function and how we try to kind of hit that little convergence point. And then all of this kind of complexity around like the relative learning rate, how frequently we update, the magnitude with which we update, it's all about trying to kind of optimize around finding a solution as effectively and efficiently as possible. So that's really a lot of what we're trying to do here. Yeah, and so, and hopefully I think I almost feel so one of the kind of the interesting things about data science today is just given the multitude of user-friendly libraries out there, I think hopefully, so guys, at this point, you've gone through 2 projects. Hopefully at this point you kind of feel relatively comfortable with the data science Python development environment. And just kind of how user-friendly and intuitive these things are. But the reality being that and so, it's so easy for us to kind of tweak little things and just adjust things like, oh, in your SVM, change your solver to SAG, change your solver to this, right? It's just such an easy input from a coding perspective. But like the underlying it, there's this really this depth and this nuance and just sort of the sheer number of kind of different ways in which you can approach a problem. And the scary thing that, more often than not, you don't necessarily know going in which one is going to work and which one isn't. And again, you can try to, having this knowledge, having this insight kind of allows you to kind of orient and generally have a good intuition for what will work and what won't. But a lot of this, you just kind of have to try out. So I guess the metaphor I'm going with here is like thinking like, oh, this is kind of easy. You plug in the thing, maybe tweak a few things, but the reality is there's just so much going on, so many kind of things that you can kind of play with and adjust in terms of having your model converge. So I think that's what I wanted to cover today. And I know it's a lot, and I'm sorry guys, because we went deep with this. I think this is going to probably be the most theoretically oriented discussion section. But I did want to kind of use the relative lapse. Like we haven't published project 3 yet, so we have like a little bit of time. And I just feel like this is so critical to like understanding a lot of like the mechanics of what we're doing. So let me kind of pause there, wolf down some of my lunch. Let me just see if you guys have any questions on all this, because I know I threw a lot at you. Yeah, okay, I'm done with that. So you guys hanging in there? You guys feeling all right with that? Okay, so I'm hearing some relatively good thing. Anything you guys want to talk through? Anything that you want to kind of clear up a little bit on this? Otherwise, we're going to go with the memes. Believe me, I don't need much coaxing to get over to the memes. Let's say how we're doing with submissions. Okay. Okay, we got some good ones. Okay, hang on. All right, yeah. All right. Let me start throwing these up onto the deck. And then in the meantime, guys, how do you choose support factors? Okay, so good question about how the support factors are chosen. I believe I don't actually have a good answer for that. It's kind of I know like when you read the description, it's like, oh, support factors are just chosen. I do know that it's not, you don't manually input your support vector. And I know it's not something like a KNN where it's sort of you define, you'll arbitrarily say choose the 5 things. I think it is chosen automatically as part of the thing. But I know it's the ones that are kind of closest to the decision curve, but I don't know how they're selected. That is a good question. Okay, so we've got, let's see, how many memes do we got come through here? Okay, we got 1. We got 2. We got 3. Some of these are looking awesome. Okay. Okay. Oh, we got 2 submissions coming. Okay, so we got a total of 4 memes that we're going to be throwing up here. Okay, give me a minute, guys. Now, to be fair, I'm just going to throw these up in exactly the order in which they were received. So I'm not going to be no favoritisms. Whoever emailed me first will get first position, but we're not going to do anything beyond that. Okay. So. Right, and then I just need to do attribution. So I'm just going to do first names just to make it this quicker. Oh man, some of these are great. You guys did great with these. Okay, let's see, and we're up to the last one, guys. Bear with me. Okay, so because Mani has two, I'm just going to just put them as separate ones, but I guess we'll just treat those as two submissions. Okay, and then can I get somebody from the chat who's willing to be the official scorekeeper for this? Okay, anyone want to keep count of the votes? Am I sharing? I'm not sharing my screen. All right. Go. Okay. All right, then I'll just count them up. That's fine. I can do. Okay. So first up, Shrinacath. That's so good, man. I love that. Okay, next up we got Rob. Now, Rob, I will just say if this one wins, we're gonna have to modify this one because I'm not putting personal names up on the gram. What's less the inside joke and it's just more I don't want to be like doxing people on public Instagram accounts. Okay, next up we got Belle. Okay, nice. Yep, KNN, just kind of the plug and chug classifier. No need to just get it in, get it done. Okay, then we got Mani with two. So if you guys are going to vote, you could just indicate like Mani 1 or Mani 2 for this. Okay, so this is like meta. It's like me in the meme being referenced as meme. Oh no, you're right. It's with an E. I'm sorry, bro. I'll fix that right now. I'm sorry. That's not okay. All right, let's get that back up on full screen. Okay, so yeah, so this is ultimate meta here. I'm in the meme and I'm being referenced in the meme too. Okay, and then last but not least, yeah, desperately trying to feed it some data. Okay, so again, let's get our votes in. We have Monic 2, Monic 1, Belle, Rob, or Shrinacath. Okay, any more votes? right, speak now or hold your peace. Let's see here we got here. So we have, okay, bell, we have two. Yep, I'm seeing, okay, it looks like, indeed. Monic 2 with 1, 2, 3, 4 votes. There's our winner. Let's pull that bad boy up. Boom. All right,
Oh,
well,
you stop sharing. We
oh
can't
no,
see
I'm
it.
sorry, what? Okay, and our winner. So my classifier just doing nothing. It's 2 a.m. I'm just feeding it data, desperate for something to happen. That is awesome vibe. And dude, we have all been there. So well done, man. You know the rules. Send me your email. And then let me know Starbucks or something else. And we'll get you your thing. I will also, on that note, I will stop recording.